Hello. So this is a follow-up to the previous video. We're going to do some conservation of energy examples. I've rewritten the conservation of energy equation, also drawn our first example down there with a block that we're going to push with a spring. If you want to pause the video for a sec and copy that down, I would suggest that. All right. So quick reminder, uh, these first three terms, that's the mechanical energy that the system has before or at one location of its motion. Um, EK is kinetic energy, EG is gravitational potential energy, and EE is spring potential energy. Work, W in this case, is work done by forces that aren't involved in those energies. So like friction or tension or applied force. Those are when we turn like thermal energy into mechanical energy or vice versa, or electrical energy or chemical potential energy. Um, and then these terms here are the total mechanical energy of the system afterward. Now, for today, well, first of all, that equation is called the conservation of energy. Energy is always conserved, and you should have seen that in all of your uh, examples and all of your labs you've already done so far. We're going to even go one step further. For today, we're going to make the W term, it's going to be zero. We're not going to have any friction today or any applied forces acting on our objects. So not only is overall energy always conserved, in this case, the mechanical energy before the object moves or at point 1 is going to equal the mechanical energy of the object at point 2. Um, now, in the first example there, we've got a spring, you've compressed it a distance x, and the mass of the backpack is m, okay? And we're going to follow the same steps we followed on the example that we did on the previous discussion. It's also the way your example or your problems are going to be laid out in your first worksheet you're going to do after this. You're expected to do these problem solving steps no matter what, whether they're outlined or not. You are expected to do these for any problem that involves conservation of energy. Okay, so step one is you write out the conservation of energy equation, only the terms that actually are occurring in this problem. So what we're going to do is we're going to figure out what's the velocity of this block after the spring has given it a start. In other words, you've compressed the spring some distance. The spring's going to push the block, and then when it's here and the spring releases it, how fast is it going? Okay. Now I'm going to give you some numbers to go with this. Let's say K is 1,000 newtons per meter. Let's say X is 50 centimeters. And let's say the mass of that, let's say it's a book, and let's say the mass is 2 kilograms. And notice it's on wheels, so we're going to not worry about friction at all. All right, so how fast is the book going after it leaves a spring? Okay, well, the two locations we're going to study, and when the spring is compressed and the book bag and the book's ready to go, and then point B is when the book's moving after the spring is uncompressed and it's released the book. Okay, well, at point A, does the book have any kinetic energy? Well, is it moving? Nope. So it doesn't have any kinetic energy. Does it have any height, gravitational potential energy? Nope. The book never changes its height, so there's no EG. Is there any springs compressed or pulled apart? Yes, there is a spring compressed, so there is an E sub E. There's an elastic potential energy. There's no friction or applied forces acting on the book, so there's no W. When the book gets to its second spot over here at point B, is it moving? Well, you're darn straight it is, so it's got kinetic energy. Is there any change in height? No, so there's no gravitational energy. And is the spring compressed anymore? Nope, so there's no elastic energy. So there's your first step, is figuring out what kind of energies are involved in this. Step two is putting in the equations for each one. So for elastic potential energy, it's 1/2 kx squared. And for kinetic energy, it's 1/2 mv squared. And then the third step is always subbing in your numerical values. So in this case, K was 1,000 and X, now be careful, it's 50 centimeters. It's going to happen on your worksheet a bunch. It's 50 centimeters. You got to convert that to meters. It's meters, and you got to square that. And that equals 1/2. The mass of the book is 2, and we're trying to solve for v. So now we're just going to do some math. You'll notice the halves will drop out. There's one on each side. 1,000 times 1/2 is 500 times 1/2 is 250. You got 250 equals 2v squared, or 125 equals v squared, and v equals the square root of 125, which is 11.2 meters per second. So that's your first example. The next example, we'll call this example 2, okay, is let's say you put the same spring on a hill, okay, and you put your book, same book, against the spring. You compress it the same distance x, so the book's got a mass of 2 kilograms, x is 50 centimeters, and the spring constant's 1,000 newtons per meter, just like before, and you release the spring. And now I'm going to ask a different question. How high does the book get before it stops? What's the height it achieves? Now, when you say height, we're talking about this dimension right here, okay? We're not talking about how far it goes. That's a different thing, and I have to give you the angle of the incline to figure that out. So for now, I just want to know the height. How high does it go above its starting point? All right, so our first step is to write out our conservation of energy equation. And it's actually the left-hand side is exactly as it was before. You have elastic potential energy to start with. We're going to go ahead and say that where this thing starts, we're going to call that height equals 0. So when it starts, there's no gravitational potential energy because there's no height, and it ain't moving yet, so there's no kinetic energy. There's no friction or anything else doing work on this thing. So what do we have when the book bag or the book gets to location B? Oh, by the way, location A is here, location B is there. All right, well, at location B, it's not moving anymore. We want to know its max height. At its maximum height, it's stopped moving. So if it's not moving, there's no kinetic energy. There is gravitational potential energy because it has gained height. So we've got an E sub G. And the spring is no longer compressed, so there's no EE, there's no elastic energy anymore. So this is our new equation. We're going to put in the equations for each of these. So EE is 1/2 kx squared, and E sub G is mgh. And then step 3 is sub in your numbers. So we got 1/2 times 1,000 times 0.5 squared equals 2 times 9.8. And this time we're solving for the height, which we don't know. And then now we're going to do a little bit of math. Let's see here. This left side will be 125. The right side will be 19.6 times h. And if I divide both sides by 19.6, you get a height. And if you plug those in your calculator, I get 6.38 meters. So that's the height that the book achieves before it stops and starts rolling back down the hill. Okay. I got one last example for you called example 3. Okay, let's say I now do the following. Let's say I got the floor. I have the same spring constant 1,000. I have the same book, mass of 2 kilograms, and I compress it 50 centimeters again. Okay, and now what I'm going to ask is when the book bag, oh, I'm sorry. In this problem here, I lied. We're going to change 2 things. We're going to make the compression 60 centimeters, and we're going to do a different spring. We're going to say the spring is 3,000 newtons per meter. Okay, and the mass of the book is still 2 kilograms. Okay, so now what I want to know is I'm going to release the spring, and I want to know when the book is 8 meters from the starting point. So when the height is 8 meters, how fast is it going? What's V equal to? Okay, so when it's up here somewhere, and it's left the spring, and when it's traveled 8 meters, how fast is it going at that point? It's still, I'm claiming it's still moving, so we're going to figure out its speed. Okay, so looking back at, I'm going to rewrite the equation for energy conservation. So we got EK plus EG plus EE plus W equals EK plus EG plus EE. Okay. All right. So our two locations are going to be point A is right at the moment we're releasing the spring before the book starts moving, and point B is up here when it's got a height and it's still moving. Okay. All right. At point A, does the book have any kinetic energy? Well, it's not moving, so no. Does it have any gravitational potential energy? Well, I'm going to call that height equals 0, so no. Does it have any elastic energy? You betcha. There's a compressed spring there. There's no non-conservative forces. There's no friction. There's no applied forces. There's no tension doing any work on this thing, converting chemical energy to mechanical or heat or anything like that. At point B, does the book have any kinetic energy? Well, I'm asking you how fast it's going, so it better have some kinetic energy. It better be moving. Does it have any gravitational potential energy? Well, you're darn right it does, because it has height, right? Does it have any elastic potential energy? Is the spring still compressed? No. Okay. So here we got an example with 3 different forms of energy. And then I'm going to go ahead and plug in my equations. 1/2 kx squared equals 1/2 m velocity squared plus mgh. Now, I can't cancel anything out here. Like, for instance, the halves, you can't cancel those out because there's no half in the last term. So you're stuck plugging numbers in for all these things. And by the way, this would be step 1 on your worksheet. That would be step 2. Here's step 3. Let's see, we said K was 3,000. X we said is 0.6. Got to square that. 1/2. The mass of the book is 2. I'm trying to find its velocity at that point, at point B. Mass of the book is 2. Acceleration of gravity is 9.8. And the height of the book, I told you I want to know how fast it's going when it is 8 meters from the start point. So H is 8. All right. And now we're going to do math. Let's see here. If we do 0.5 times 3,000 times 0.6 squared, I get a 540 here. This equals 1/2 times 2 is just 1, v squared, plus here I get 156.8. So if I subtract that from both sides, I get v squared is 383.2, and I get the velocity is 19.6 meters per second at that point. Okay, so I hope those examples help. You definitely want to do the same problem-solving steps on the sheets, and even when these problem-solving steps aren't explicitly listed for you, you still want to do them every single time. All right, good luck, and hope you do well.